Okay, so I'll try to advance the slides again from here. There is a short movie in between. If you can't see that clearly, please do let me know.
Okay.
Great. So now I'll talk about the search for EM counterparts. And as the name says, I'm actually going to focus more on the search itself rather than the electromagnetic counterparts. For completeness, I will talk a bit about what counterparts we expect, but I've not put in a lot of details. So if any of you wants to discuss that, then we could do that during the questions at the end. So the outline is I'm going to talk about AstroSat for continuous wave sources and transients, the new telescope growth which we are going to put up. And finally, in this talk comes the fun part, the challenge that I was going to put out. So, what kind of electromagnetic counterparts do we expect for gravitational wave sources? Well, broadly, you could divide LIGO sources into burst and continuous wave. So, for the burst sources, you can expect electromagnetic counterparts unless for a large variety of them. Even for supernovae, for example, the electromagnetic counterpart is expected to be a lot easier to detect than the gravitational wave source. Then, if you have binaries, compact binary coalescences, if there's a neutron star involved, then again you expect some electromagnetic counterparts from that. The case which most people discuss in great detail is a kilonova, which excuse me, which would arise from the merger of two neutron stars. Now, looking at the various radiation mechanisms that would be involved in this, if you start with the merger of the two neutron stars, uh, we expect that these are the progenitors of short-haired gamma ray bursts. So, if you happen to be perpendicular to the plane of the orbit, you will see a short GRB, which could have emission for seconds in X-rays, hours to days in optical, and weeks to years in radio. But that is not it. If you actually look at the simulations of the merger process, you expect that there will be a equatorial disk that is formed, and that disk itself will be extremely neutron rich. These disks are expected to be the main source of R process nucleosynthesis in the universe. And actually, curiously, the models for emission from this disk are limited by our knowledge of electronic transitions in lanthanide series elements and so on, because never before has anyone had to worry about them in such detail. But we do expect that it will have a rather red transient called a kilonova, which would have a timescale of order of a day to a few days. Again, different models predict slightly different things. But apart from that, you could then have all of this ejecta shocking the circumstellar medium or the interstellar medium, and this shock is what you would expect to give rise to radio emission. Now, this would peak anywhere between months to some models even predict years after the kilonova, after the BNS merger itself. So yes, the radio timescales, as we discussed a minute ago, can actually be rather slow. And this is a standard radio emission, so again, you expect that lower frequencies will peak even later. What is important is that, in contrast to the GRB itself, the kilonova and the radio emission are expected to be nearly isotropic. But these are all expected to be faint for a typical LIGO source at, say, 100 megaparsecs or so, based on which model you like. The kilonova may peak at anywhere between 20th to 24th magnitude. 24th magnitude would put it well beyond the reach of meter class telescopes around the world. Okay, so before going into optical, I'll actually like to start with AstroSat. We have discussed AstroSat to some detail already. At the bottom now, I've added the AstroSat website, astrosat.iuca.in. If you want to know more details about the satellite and its instruments, then just go to this site. There's a handbook, which has nice details about the capabilities and sensitivities of all the instruments. Uh, what I'm going to talk about now is CZTI, which is this instrument in the front corner here. This golden panel here is actually a radiator plate to cool the detectors. And this is the widest field instrument on AstroSat. The wide field is still about 20 square degrees in the primary field of view. But what I've plotted here in these two maps is all sky sensitivity of CZTI at various energies. And we call this as effective area. The physical area is about 500 square centimeters, and effective area is the physical area multiplied by any projection terms and any efficiency terms that you may have because of absorption of X-rays by various intervening surfaces. So what we can see is that over about 1/3 of the sky at energies above say 100 keV or so, CZTI actually has a pretty large effective area. So we can see sources from which are far outside our field of view, and we can detect them with good sensitivity. If these are transient sources, if this is a flash of X-rays, then that makes analysis even easier because you can take a background sample from just before the flash or after the flash, and that allows you to very easily isolate photons which came from this source. A great example of this was that on the first day when CZTI was activated, within a few hours we had a gamma ray burst which was about 60 degrees off axis. Okay, so these two arrows show the projection on different planes. So the transient happened somewhere in this direction. It was detected by other satellites as well, and it was very clearly detected by CZTI. I will show some detection plots much later in the talk. And not just this, this actually allows us now to give, anytime we receive a trigger from LIGO, we can actually start scanning our data to see if we had any coincident detections. And here is my all sky coverage map for the first source. This is GW150914. And you can see that we have great uniform sensitivity across the entire sky, exactly equal to 0, because AstroSat was still sitting in a box in Sriharikota when this transient happened. Things got a bit better for the next event. This is GW151226. At this time, we had been operational for a couple of months. We understood the instrument pretty well. I have taken the previous all-sky map of sensitivity and projected into array coordinates now, so projected it into the sky frame. These areas here are actually shadows of different instruments aboard the satellite. We have become even better now, and we can actually see through these areas and analyze reasonably as well. If you compare this with the sky map, here is the localization map from LIGO. We observed about the red part is what we could see. The blue parts of the localization are things that we could not see. So we had good sensitivity for about 1/3 of the localization region for GW151226. And the upper limits that we've been placing are actually pretty competitive with BAT, Integral, and even Fermi. In fact, we are more sensitive than these instruments in several of the events. So CZTI, while it was not designed to be a wide field transient instrument, is proving to be great in this context. This animation is a simple spherical curve in vacuum approximation of AstroSat. The yellow box is CZTI. And all the black arrows show the various gamma ray bursts that we have detected so far. So you can see that there are actually a few bursts that we have detected shining through the entire satellite. They are coming into view around now at the bottom here. So we really have good sensitivity over the entire sky. We lose about a quarter to a third of the sky to Earth occultation because we are in low Earth orbit. But if there's a bright flash anywhere in the sky, there's a very good chance that we will see it. We have seen about 105 gamma ray bursts in the year and a half that we have been operational, or 541 days, 0 hours, 43 minutes that we have been operational so far. Transient sources are what we usually all tend to talk about, but that's not all that LIGO, of course, is interested in. If you have accreting neutron stars, these are continuous wave sources, and they are also great X-ray sources, so good to be monitored by X-ray satellites. What happens is as the accretion rate varies, the rotational frequency of these neutron stars changes over time. And these changes are quite unpredictable. You can have spin up because you are getting more matter. You can have spin down as all of that energy is lost. It all depends on the exact accretion circumstances of the source. Now, if you want to do a phased search in LIGO data for these sources, then you need to accurately know the frequency as a function of time or the rotation period as a function of time, for which you need regular monitoring observations of these sources. So this could be attained by either LAX-PC or by SSM. So here is the large area X-ray proportional counter LAX-PC. This is one of the 3 units. These are sensitive from a few keV to about 80 keV, great energy resolution, and by far this is the best timing instrument that has ever functioned in in um, in X-ray astronomy. So you could actually propose for targeted observations of LIGO's favorite list of sources and keep monitoring them, say every 15 days, to keep getting the period, and you stack that up, you phase them up together, and you use that as a ephemeris for the LIGO sources. But apart from that, you could actually even get some of this data for free from just the regular scanning sky monitor observations. So here are SSM detections of period in 3 of the bright sources. All 3 are pulsars: SENX3, Vela X1, and 4U0115. What has been shown here is that in just the regular SSM observations, which usually consist of a 15-minute stare, you can actually detect the pulsations and the period pretty well. So, for a set of bright sources around the sky, you could actually just mine SSM data, keep getting the periods, phase them up properly, and provide that as an input to the LSC for searches of gravitational waves from these sources. Okay, this was probably discussed by Sukant in some detail in his talk. LIGO sources have a large positional uncertainty. The first event, for example, had a 90% containment region of about 600 square degrees. It's common to have these containment regions spanning thousands of square degrees actually, which makes it pretty difficult for ground-based telescopes to follow up such sources. A typical meter-class telescope has a 10 to 15 arc-minute field of view, so about zero point 0.1 square degrees, which would make it impossible to tile this entire region. One solution to that is that you make a global network so that all observatories can work together in order to follow up these sources. And one such attempt is our project called Growth, which is a global relay of observatories watching transients happen. This is a 7-country, 15 institute partnership. The main workhorse will be ZTF, which is being commissioned or being built at Palomar right now, which will be a 40 square degree optical imager. But the idea is that you could imagine the Earth spinning in this plot, and as various observatories go into nighttime, they can keep observing whatever sources are of interest to you. Under this project, we are building this new 0.7 meter robotic telescope at Hanle. The aperture is modest, but we make up for that by having a wide field, a 1 square degree field of view. This will be India's first fully robotic telescope. You could think of, you could consider kilonovae studies as a particular case. So if you have T0 is the trigger time when you had a merger of 2 neutron stars. Different models based on the amount of free neutrons in the disk and the opacity, which is not very well known, would predict different characteristic time scales. There are still some models which predict that kilonovae would last only for a few hours. There are models which predict that they would last for a few days. In order to be able to differentiate between these events, here's a example again where you have observations from California and Hawaii, which is where a lot of the active groups that work on transients are based, basically continental US. But after that, you would otherwise have this big desert uh, in this part of the globe. This is the Pacific and Asia regions of the globe. And if you don't have good follow-up capabilities in this part, then by the time you come over to the transient again, you will simply have a non-detection 24 hours later, and you wouldn't know if the model A or model B were correct. But you can make up for that by actually having observatories spread around the world so that you can get intermediate observations and continuous observation um, to differentiate between these different light curves. So the Growth India telescope will be India's first fully robotic telescope. Orders have been placed. We are expecting the camera to arrive in a few months from now. The telescope itself will arrive around September, and we expect that it will have enough sensitivity to go to about 21st magnitude in 5 minutes, which is good for kilonova kind of observations. And we want to commission this telescope within this calendar year itself. Okay, that brings me to the last part of my talk. We are doing reasonable on time, I think, and this is about the challenge that I was wanting to discuss. This is about finding transients in X-ray data. Okay, so let's start with raw data from AstroSat. This is the rawest form of data that you could have. What I've plotted is in a single orbit, the count rates in a single quadrant of the cadmium zinc telluride imager CZTI as a function of time. The red lines mark the regions where data are completely useless. Okay, and it is in some parts, for example, at the center here, it appears like all the data are useless. That's not quite the case. The resolution of the plot is not enough to show gaps in between. And the reason why we are seeing a lot of noise dominated parts is that astrosat is in low Earth orbit. So we often have energetic particles hitting the satellite, which gives rise to a shower of secondaries. And we detect dozens of photons in a 20 or 40 microsecond window, whereas from Poisson statistics, you would hardly expect anything there. But we know what this is, so we can clean it up on board itself, and we are getting better and better with this as time progresses. So what you see here now are cleaned data sets from two quadrants of the four identical quadrants in CZTA. At the bottom is quadrant C, where you can see a reasonably clean light curve, and at the top is quadrant D, where you still see some of these noisy spikes. Now CZTI has, each quadrant has 4096 independent pixels, and space is an unforgiving environment, so these pixels do misbehave occasionally. Each pixel has its own readout and so on. So pixels become noisy from time to time, and we have to catch that in post-processing, excise some data there. But if we are lucky and if data are well behaved, this is data from an orbit that I downloaded last night. So you get pretty good data. The background actually rises a bit. If you look at the bottom plot, it rises a bit around 2000 seconds, then again around 7000 seconds. What is happening here is that there's a region of anomalous magnetic fields above the South Atlantic Ocean, which is called the South Atlantic Anomaly, extremely imaginative name. And there are a whole lot of charged particles which are trapped in those magnetic field regions there, which leads to a very high background count rate as you enter those regions. And that is what is being seen here. So around 1000 seconds when we are entering the SA, the background rate starts to shoot up. In order to avoid physical damage to the detector, we actually switch off the high voltage, otherwise you would get shorting. And then when you emerge out of the SA just under 1000 seconds later, we switch on the detectors again and you have this. The middle squished plot is the bottom plot again, but now plotted at the scale of the top plot. So just to show you that here, while I'm going from a typical count rate of about 400 counts per second up to about 1000 at peak here. Here on the other end, I'm going from 400 all the way to nearly 4000 counts, which is the maximum that we can read out, 3000 and some. So now what we want to do is that within this data, okay, we have to look for a transient. And the way a transient would look is very similar to this spike that you see here at about 4000 seconds. Okay, so the question is, how do you differentiate between a real transient and a fake source? Before I show you some methods that we use, here is what final clean data looks like. Even from 400 counts per second, the on-orbit cleaning that we do is purposely conservative. In ground processing, we further reject a lot of noise and we come down to about 100 to 120 counts per second. You can see light curves for the four quadrants plotted over here. You can see that quadrant 3 is showing some of these dips. And these actually correspond to saturation, where a pixel became so noisy that data from that quadrant filled up the frame every second. So we lost some events. And you can see that data are reasonably Poissonian at this point. The red plots, I've been a bit lazy. Instead of doing a proper fit, I've just scaled the Poisson plots to the peak of the histograms. So the quality of data are reasonable when we come to this stage. And the way we've been looking for transients so far is by making dynamic spectra or time energy plots. So if you look at raw data, then we actually measure every single photon individually. For every photon, we know the time of arrival of the photon with about 20 microsecond accuracy. We also know the energy of the photon with about 10% uncertainty, depends as a function of energy again. And we know what pixel it landed on. But the way the detector is designed is that the pixel where a photon was incident does not directly relate to its the position of the source on the sky. So what I've done here is on the x-axis I have time, on the y-axis I have energy. In each 20-second window, I have taken all the photons from that window and calculated a spectrum and plotted it vertically. And you can see that the data are reasonably stable over time. And at about 700 seconds, there's something weird happening. I can project this plot along the x or y axis. If I project it downwards, then I get a light curve. And you can see that the background count rate also shows some variations. These are not just Poisson variations, these are also orbital variations coming from how close you are to the SA and so on. If I project it along this axis, then I can see the mean spectrum here, which and you will see that the total counts actually vary quite a bit. At higher energies, I have about a few hundred counts, whereas at low energies, I have a few thousand counts. So what I can do is, if I want to search for transients, I can get rid of this steady background. So I subtract the median from the data. And you can see that the differences on this scale now are actually quite small. I have not put in a color bar, but the peak here would be a few hundred counts, which is a lot less than the few thousand that we had before. Actually, you can not even a few hundred, sorry, a few tens of counts, which you can see on the light curve here. And the transient starts showing up a lot better than the previous plot. I've taken a very obvious GRB. This is actually the first GRB that we had detected, which I showed the location plot in one of my early slides. What we then do as a final step is we actually, at each energy, we calculate the sigma of the light curve and we deviate it by the sigma. And you end up with, so now the color bar here, the color scale here is showing you some kind of a significance measure. For instance, although the transient itself gave more photons at low energies, which you can see here, there's also a lot more variation in the typical count rate at low energies. So although you have a lot of photons, this is not very significant. On the other hand, in 120 to 150 keV kind of range, the background is a lot more stable. So in this range, although you had fewer photons, the significance of those is a lot more. Now these searches we currently do manually. Anytime we get a trigger from any other instrument, for instance, we actually go and look at the data. There's a grad student who does this every single day. And after this stage, if we have a strong visual detection, we actually go for, we check that since we have 4 independent and identical instruments, we want to see if this was detected in multiple quadrants. Based on where the source was in the sky, you might see it in only 2 out of the 4. And then for LIGO, we of course have only non-detections so far. Then what we do is we take nearby orbits. We usually take about 10 nearby orbits, and we calculate only the count rate as a function of time. We subtract, we detrend the light curve to get rid of any orbital variations. And from that, we actually measure, we set a false alarm rate saying, okay, if we are searching for a transient in say 1,000-second window centered on the time provided by LIGO, we want a maximum false alarm rate per quadrant of 10%, which would give us a combined false alarm rate of 1 in 10 raised to 4, which is highly acceptable, 99.99% confidence. So since the data are not completely Poissonian, what we do is instead of just taking a mean and sigma of some sort, we actually look at the data, we make histograms of nearby orbits, and from that we decide that, okay, in a random 1,000-second window, there's only 10% chance that CZTI light curve will show you more than X counts. And then since you have 4 independent quadrants, the probability of all 4 quadrants going above that threshold in a given window is 10 raised to minus 4. So this is how we are doing our searches right now. What I want to get to is how can we automate this process? This should be amenable to a lot more statistical techniques for analysis. We should also, for example, if we assume a typical spectrum, a GRB-like spectrum, we should also be able to incorporate that rather than using just count rates in our upper limits. And that should actually, I suspect that it might push our upper limits down by a factor of 2. So this is the question that we are working with just now. There are some attempts that we are making, but I'll leave you with that, and I can take any questions. Thank you.
Thank you very much, Varun. From the face of it, this problem looks like very much like transient detection problem in gravitational astronomy. Right, this time frequency detection techniques are very similar in both cases. Any questions?
In some sense, Ajit, it is actually simpler because I'm not looking for frequency change as a function of time. This is all going to happen at a single time. The only reason why we separate it by energy is that unlike the case I have shown, we also have transients which are detected only at low energies or only at high energies. So this could be something that is done with that could be done with a 2D Bayesian block kind of setup. We also have to repeat this search at various transients at various time scales. If you have a burst of say 0.1 second duration, then it will be completely wiped out in a 10-second duration search. So based on physical motivations, we repeat these searches by binning data at 0.1, 1, and 10 seconds.
Yeah, so I should clarify that. I meant the non-chirp burst searches basically that in LIGO, which does not necessarily have this frequency evolution like supernovae or so.
Correct.
Any questions, Varun? So, Varun, another question. So, for these cosmic rays that are hitting the instrument, do you have any other witness instruments that are used to sort of use for data quality cuts?
We do have an anti-coincidence detector, but that will not detect these because what is happening is that these are protons which are hitting the spacecraft. And they are locally creating a shower. So if you break data into 20 microsecond chunks, then in a typical chunk you expect 1 photon, maybe rarely 2 photons, but suddenly you'll see 20 photons, and they show geometrically correlated nature, and they are all at low energies. So we have telltale signatures that these are happening locally, but there is no other witness instrument because essentially all the proton energy has been converted into these low energy photons which get completely absorbed by our top detector. On the other hand, if the proton went through our X-ray detector and continued forward, it would hit our anti-coincidence detector, which sits right below our primary detector, and that is something which we do use to reject particle events. But these are photon events. The particle interaction happened with the satellite.
I see.
Integral has seen similar issues in their data, for example.
There are no further questions. Let's thank Varun again. Thank you very much, Varun.
Thank you.
So we'll break for coffee now, and we will come back at 11:30.